Thank you, and good morning, everyone. So the last two lectures, we talked about some basics about early universe cosmology, so particularly CMB decoupling and Big Bang nucleosynthesis. And then last lecture, we talked about baryogenesis, and we continue our journey to even earlier times. Today and tomorrow, we'll be talking about inflation. Today will be the background evolution, which will help us to understand the dynamics of the entire universe, in particular the expansion dynamics of inflation, and how we can realize that in a particle physics model. And then tomorrow we'll talk about the perturbations, quantum perturbations during inflation, which will lead to some of the key observables that we have today. So I'll be trying today to do it on the tablet, in the hope that you can read better here than you can read it on the whiteboard. We'll see how it goes. We had some technical issues setting this up. It's not perfect. And then at the end of today, I'm going to ask you what actually worked better from your point of view, and then according to that, we'll do whatever you prefer tomorrow. Okay, so the reasons we think about inflation in the first place are a few. One of them is the so-called flatness problem. That's one that you have on the exercise sheet. It's about explaining why the universe as we observe it today seems to have zero curvature, or very close to zero curvature. One possible explanation for that is inflation. So I won't go into that particular problem and its resolution today, because we have that on the exercise. Instead, what I want to talk about today is the horizon problem. So let me briefly tell you what that's about. So what we want to do is we compute the past light cone, the region of causal contact. So the question is, we are here today, we observe the universe. What is the past light cone that we observe? And to do that, we induce conformal time tau. So tau is, so d tau is a dt. And you see immediately my handwriting is a lot worse here than it is on Blackboard. So tau, if we want to compute the past light cone, we have to integrate from 0 to t over dt prime a of t prime, right? That's just basically the definition of tau. We can d tau is a dt. Ah. Right. Okay. No. Okay. Okay. This is a bit tricky. So this. Okay. So this is the definition is correct. And this is also. Now let me think. Now you've confused me. Right. Yeah, dt should be a d tau. Yeah, of course. Because we write, thank you. We write the metric, of course, just as dt squared plus a squared dx squared, right? And now we introduce the d tau squared, we take the a out front, and so it's the other way around. So we have dt is a d tau, thank you. First equation wrong, good start to the day. Okay, so now we understand what I'm computing here with the tau, right? So now we can use the fact that Hubble is a dot over a, just the definition of Hubble, to write this is an integral over dA. So we're at integral 0 to a dA h a squared. And you see from the fact I'm putting 0 here that I really want to compute the entire past last cone all the way to the singularity, right? All the way to time 0, which is where the size of the universe is 0, concretely meaning the scale factor is 0. We can rewrite that as an integral over d ln a over 1 over ah. And now 1 over ah, again by definition of Hubble, is nothing over 1 over a dot. So what does that mean? If you recall the second Friedmann equation, so what we called F2, second free-run equation said that A double dot is minus 1 over 6 A rho 1 plus 3 omega, where omega was the equation of state. And that is in particular negative for all omega larger than minus 1/3. Meaning in particular for omega equals 0, which was matter, and omega is plus 1/3, which is radiation. Okay, so this means decelerating universe, a double dot negative, right, which makes sense. Kind of you have some initial explosion, some big bang, right, and then you just have matter and radiation, which means, yeah, you can accelerate, but you have a decelerated expansion. You can expand, but with a decelerated speed. But if a double dot is negative, that means that 1 over a dot, meaning 1 over AH, is increasing, right? Because a dot is decreasing. So that means 1 over AH increases as A increases or time increases, right? So as universe expands and T expands, we have this argument increasing. Which means that the fraction of the universe which is in causal contact increases continuously with time. That's what we compute out of that. And then you may say, okay, this is kind of intuitive. Of course, the fraction of the universe that we can see, of course, our past last cone increases with time. But the fact that you find that intuitive is simply because in your mind you are actually thinking about a universe which has a decelerated expansion, because you're thinking about a universe which is matter or radiation dominated. You can see from the second Friedmann equation, if the omega is not larger than minus 1/3, this is not necessarily the case. Then the past light cone actually shrinks. But in this case, we have that, okay, now if I write text, let's see. So fraction of universe in causal contact increases. Okay, so what does that mean? That means in particular, if we look at the CMB, that if we have a time axis, we have an observer here, that's us, and we are observing our past light cone in the past all the way back. At some point there's the CMB. So this is the CMB as we see it. This is the picture of the anisotropies as we see in the sky map. But then at some even earlier time, there's our time 0, right? Where the universe, just according to Friedmann equations, if we assume matter and radiation dominated at size 0, and that means that every point in the CMB also has a past light cone, like this, and so on. And in particular, it means that the different one point of the CMB here and one point of the CMB here, their light cones in the past never overlapped, right? Meaning there's absolutely no way in a universe that has the condition omega larger than minus 1/3 that any information can be exchanged between this patch of the CMB and this patch of the CMB, right? There simply wasn't enough time in the past for them to exchange information, even if the information could go with the speed of light. And that is a mystery, because that means that we don't understand why the CMB can have the same temperature everywhere, or to very good approximation the same temperature. How can two different patches of the universe, which were never in causal contact, we did not have any chance whatsoever to exchange information, how did they agree to have exactly the same temperature? So in a universe which is matter and radiation dominated all the way back to time equals 0, you cannot explain why the CMB is so homogeneous. So then, of course, from what we've done here, it's kind of clear where do we make an assumption, right? We made an assumption when we put this condition here. And this is precisely the condition that we need to violate if we want to find an explanation why the CMB could be so homogeneous. So this works. Okay, magic, right? So I can still cheat, right? Even though I'm doing it here. So the CMB, as we observe it today, consists in this picture of about 10 to the 5 regions, which can, with the condition omega larger than minus one third, not be in causal contact. And yeah, this is then the question: how can they all have the same temperature? And the same issue is with the flatness problem. The flatness problem is one of your exercise, and also there you will find, again, making the exact same assumption. So assuming we have a decelerated expansion of the universe, you cannot explain why the curvature is so small, unless you put in some absolutely horrible amount of fine-tuning. So this is why, this is two of the motivations, there are more, but this is two of the motivations why people have started thinking about exotic state in the early universe, which has a value of omega, which is smaller than minus one third. Are there questions on that so far? Yeah.
So yesterday we were talking about the possibility of having in a universe in which there is more matter in one side and more antimatter in another side, and you mentioned that when we consider inflation as an initial condition for the CMB, then this wouldn't be let's say a good proposition, and it's because of this same idea that eventually inflation can explain homogeneity in the CMB, so we will expect the same kind of homogeneity between matter and antimatter.
That's one way to argue it. I can argue it in a better way at the end of this slide. There'll be an even better way to argue it once we get to the end of the slide.
Okay, thanks.
Yeah, another one up front.
We have not only the flatness problem and the horizon problem. We have also the possibility to have relics from the early universe. Also, maybe the inflation could be solve this, right?
Yeah, and again, why it solves that will be clear at the end of the next slide. Yeah. Okay. So we need something which is an equation of state which is smaller than minus one third. And that something cannot be matter and not be radiation, right? So let's think of kind of a different possibility to get different equations of state. And to do that, let me write down the most simplest particle physics model, basically chapter 1 of Peskin-Schroeder, which is just a single real scalar field. So the action, so to excuse my bad handwriting, my pointer is off by 0.5 centimeter from where it's supposed to be, so whatever. So the action, we have minus determinant of the metric. Ritchie scalar, I'm setting, okay, we can put in a blank mass. Then we have the kinetic term for our scalar. And we have some potential term for our scalar, which I won't specify now. And so this, okay, the first part of this is just the Einstein-Hilbert action, and the second part of that is the action from a scalar field. Okay, so to get the equation of state, we need pressure divided by energy, right? So we need to compute the energy density and the pressure. So to get the energy density, or to get the entire thing, right, we need the energy momentum tensor, which we can get just by variation of the action, more precisely as minus 2 square root of minus g, and then variation of the action with respect to the metric. Okay, so if we vary with respect to the metric, we have, of course, the kinetic term here. That's rather trivial, right? So then we just get the part at the back, right? So del mu phi, del nu phi. And then we have, however, also the determinant of the metric up front, right? So we also need to perform the variation with respect to the metric here. And that gives, from the variation of this term, we get g mu nu. And then we're left with the inside of this bracket. And And I should say here I'm just varying the phi action because I would only want the energy momentum tensor coming actually from the scalar field, not from the Einstein-Hilbert term. So then I have 1/2. I need a new index. So del sigma phi plus V. And that, if we think that we can describe this as a perfect fluid, should be some diagonal matrix with rho minus P, and minus P. And we're going to now make a simplifying assumption. We're going to assume that phi is homogeneous. So phi of x and t is actually going to be only phi of t, which means we can drop all the spatial derivatives. And then we can just get the rho component here by just taking the 0, 0 component. Okay, so we get 1 phi dot squared from up front. And then recall that the metric was minus plus plus plus. Okay, so you get 1 minus here, 1 minus here, 1 minus here. And then in total you get, for rho, you get 1/2 phi dot squared. And then with this minus and this minus, this stays a plus, so plus V. And for the pressure, we now take the spatial components. But again, recall that we're going to drop the gradient terms, right? So the only spatial components that we get are from taking the II component in this metric, and then the 0, 0 component here. So we get, for the pressure, 1/2 rho dot squared. And now because we have the plus in the metric, we get minus V. So that's enough now to compute the equation of state. So omega P over rho. Okay, just plug this in here. So 1/2 phi dot squared minus V divided by 1/2 phi dot squared plus V. And now you see that if the potential energy is much bigger than the kinetic energy, right, then we can drop this first term and we just get omega goes to -1. And -1 is clearly smaller than -1/3. So we found a very, very simple particle physics model, which actually gives us this weird equation of state, right, which kind of corresponds to negative pressure. And that's, so yeah, so this is -1/3, right? So this is what we wanted to, smaller than -1/3, which is exactly what we wanted to achieve. Okay, so now we see that we have something which is dominated by a potential energy, or something which is dominated by a vacuum energy. We can, in a very simple way, realize an equation of state which actually is smaller than -1/3, which means it can resolve the issue with the CMB, it can resolve the issue with the flatness problem. The way it basically does it is that if you look at then the equations of state, which we'll put or the equation of motion for the scale factor, which we'll see in a second, is that it basically extends the past light cone from t equals 0. Like it pushes the t equals 0 point back to -infinity, giving the different points of the CMB enough time in the past to actually get into causal contact. And you'll see in a second why it does that. Okay, so now we have our equation of state. What does that mean for the equation of motion for the scalar field and for the evolution of the scale factor? So to get the equation of motion for the scalar field, okay, we can just do Euler-Lagrange. So del S del phi minus del mu del S del phi mu. So this is the variation with respect to the derivative. Okay, so let me factor out a factor of -g. Then just from this first term, we just get the only thing that depends on phi is the potential. So we get minus v phi, so derivative of v with respect to phi. And then we have the kinetic term. So here we can't factor out the -g, so let me put it back again. And then we need to take the derivative of -g del mu phi. And the reason, of course, that I'm keeping the metric, right, is because we want to do Friedmann, Robertson, Walker, so there will be a time dependent in the metric. Now we make the same assumption again that phi is homogeneous, so we can drop all spatial derivatives, and then this just, okay, so this entire thing is 0, and then it simplifies to phi double dot plus 3h phi dot plus v phi equals 0. With here we have the Hubble parameter, of course, right? And the Hubble parameter is given by the energy density, which is 1/3, 1/2 phi dot squared plus v, which is, to good approximation, just 1/3 over v, if we're really in this limit that omega approaches -1. Which in particular means that, to good approximation, the Hubble parameter becomes constant during inflation. Okay. So what does this mean for the scale factor? So if you just recall the Friedmann equation, right? So we had h is a dot over a is 1/3 over rho, which is in particular constant, right, as we saw above, in the case that omega is -1. So if omega is -1, we can just solve a dot over a equal constant, right, and we just get a of t, scale factor as a function of time, is proportional to e to the Hubble times t, where Hubble is approximately constant. And that means an exponentially expanding universe. That kind of explains why the point t equals 0 is now at -infinity, right? Because if we go back in time, we have now the scale factor which is exponentially decreasing, but that means it never actually gets 0, right? It just gets arbitrarily close to 0, which is why the CMB photons or the CMB patches have now basically an infinite amount of time to actually talk to each other in the past, which is why they can get into causal contact. Now you may say, okay, this is a weird trick, right? I mean, this is just some math thing happening, right? Where's the physics in this? But recall that the initial singularity, right, was also kind of just an artifact of our equations. The initial singularity was simply the 0 point in our equations because we assume matter radiation domination, right? Now we simply include more general equation of state, and we see that the singularity is actually not a real singularity. This is also why inflation addresses any issue of relic particles from Gaussian theories or so, right? Because exponential expansion means whatever you generated will be exponentially diluted. And hence, there's no relics left in our present universe to worry about. This is also why it helps, or why it basically gives us initial conditions which cannot prefer matter over antimatter, because imagine you generate some amount of asymmetry in the early universe, say in terms of particles, right? So in terms of a gas of relativistic or non-relativistic particles, this entire gas is diluted exponentially to the point that the universe is really completely empty. There's really just vacuum energy left. And in vacuum energy, there's a priori no asymmetry between particles and antiparticles. So it's basically the dilution aspect of inflation, which kind of makes it such that at the end of inflation, you really have an empty universe, a clean piece of paper, and you kind of have to start generating everything from scratch. Coming back to the conformal time, which we'll need it later, right? So the fact that the scale factor behaves in this way, and now if you use the correct definition, right, between t and tau, then you get that this implies that tau goes as -1 over AH. Now, A is positive, the scale factor, Hubble is positive, right? So this means that the conformal time during inflation runs from -infinity to 0. As a bit of a convention, right? I mean, the 0 point, of course, is not actually really defined, right? Because you only define tau ever as differentials. But this is kind of the most common convention. So what we arrive at the end of this is that we have that a single scalar field achieves at generating an equation of state of the universe which is close to -1. It gives us an accelerated expansion dominated by vacuum energy, and the scale factor is evolving exponentially, diluting everything that might have been in the universe before inflation. Are there any questions so far? Okay. So now if we want to, now we want to actually compute stuff, right? So now we get the idea, but we actually want to compute predictions from inflation. And to do so, it is useful to introduce the slow roll parameters. So the idea is that we saw in the limit that the kinetic energy is really completely negligible compared to the potential energy. We get an equation of state of -1. Everything is dominated by the potential energy, and everything is constant. If that were the end of the game, inflation would never end, right? We would always be stuck in this vacuum-dominated phase. So we do need some sort of evolution. We do need some kinetic energy. It just cannot be too big, otherwise we don't have inflation anymore. So to parameterize that, we introduce these small parameters. So epsilon is introduced as h dot over h squared, and which you can rewrite using the slow roll equations. You can rewrite it as phi dot squared over h squared, using the equation of motion for the scalar field, or the energy density for the scalar field, and using the Friedmann equations. And in particular, you can show that, again, using the Friedmann equations, that h dot minus h dot over h squared smaller than 1 is exactly equivalent to demanding that a double dot is larger than 1. So demanding an accelerated expansion in the universe. And the smaller epsilon is, the closer, basically the smaller the kinetic energy compared to the potential energy, and that means the closer we are to really an equation of state of really exactly -1. No, h dot is negative, right? Because the energy density, h is the energy density, and it's slowly decreasing over the course of inflation. Because we do want to roll downhill, we cannot roll uphill. Yeah, so epsilon is positive. Eta, on the other hand, there should be actually absolute values here. Eta can be positive or negative. So eta is, epsilon just tells us really we need epsilon smaller 1 to be in an accelerated expanding universe. It's basically equivalent to the condition omega smaller than -1/3. Eta tells us that we actually want to stay in this state for a sufficiently long time. So eta contains the second derivative of phi, right? Here we have the first derivative of phi. So eta tells us that epsilon should not be changing too rapidly because we need a prolonged phase of inflation. It's not enough to kind of, at some point, rapidly move through my scalar potential and at one point kind of fulfill this condition. No, I need this for a sustained amount of time. And this is what the second slow roll parameter tells us. Now, in practice, in order to compute these slow roll parameters, you would need to already have solved the equation of motion. So you would need to already know what is h dot, what is phi dot, what is phi double dot. In practice, it's for this reason, it's more convenient to work with what is referred to as the potential slow roll parameters. So here we again define an eta, an epsilon and an eta with subscript v. And here they are now defined in terms of derivatives of the potential. So epsilon is given from the first derivative of the potential, and eta is given by the second derivative of the potential. And to very good approximation, this epsilon, like if we're in the regime that these parameters are actually small, this epsilon, to good approximation, corresponds to this epsilon, and this eta we can get just by taking the difference of this eta and this epsilon. And these are more useful to work with because you only need to know the potential. You don't actually need to solve your equations of motion to get these slow roll parameters. Okay, and then if we're in the limit where these parameters are small, then we can go back to our equation of motion on the previous slide, which had phi double dot plus 3h phi dot plus v dv d phi equals 0, We can drop the phi double dot term, right? Because that's directly the eta, that's the approximation that is small. And we end up with this very simple equation for the equation of motion of the scalar field. And we end up with the approximation that Hubble is approximately constant, and as we saw beforehand, that the scale factor grows exponentially. And this lower approximation is what will be used most of the time when one works in inflationary models. So one is really back to solving extremely simple equations. Okay, so how does this look like very concretely? So let's put the simplest potential that we can imagine, just m squared phi squared potential. And then let me just compute very concretely how inflation works in this model. To do so, I want to first introduce a new time coordinate. I mean, we already have tau and t, right? But that's not enough. That's too easy, right? So we need also want to introduce n, number of e-folds, which is defined as minus h dt. So this minus sign indicates that this is convention, right? But it indicates that this time coordinate will run backwards. It will be 0 at the end of inflation, and will take positive values before the end of inflation. And this is, of course, nothing else than dA over A, which means that if the name of this new variable is e-folds. It measures the Hubble times elapsed to the end of inflation. So if we have the scalar field in this m squared phi squared potential, I can now measure times actually in 3 ways. I can measure times by t, by tau, by n, and also by phi, because if my field is just rolling down the potential, then each point of time will correspond to a certain field value phi. So it would be useful to establish the connection between these different variables. So I want to know, for a given value of phi, a given point in my scalar potential, how many e-folds is that away from the end of inflation. So this is n of phi, which is according to the definition of n. This is the log of a scale factor at the end of inflation versus the scale factor at some time a, which corresponds to whatever the value of phi is. Then this is just, again, with the definition of n. This is minus h dt, where t goes from time t, which corresponds to whatever the time of this phi of t, to the end of inflation, t end. Okay, we can also write this as an integral over phi, right? I said phi is also a time variable here. Phi over phi end, h over phi dot d phi. And now you recognize that this thing here, h over phi dot, is basically up to factor 2. This is square root of the epsilon that we introduced on the previous slide. So I can write this. I'm absorbing the minus sign, changing the integration boundaries. Phi n over phi, 1 over 2 square root of 2 epsilon d phi. And why I do this exercise will become clear in a second. Okay, and now to actually, I told you that with this accelerated phase of expansion, we can solve the flatness and horizon problems. Now, of course, we need a sufficient amount of accelerated expansion to do it. If we have some very short period, it will just simply not be enough to do the job. So what we need is a roughly that from the end of inflation until whenever inflation started, we need at least something like, the details depends, can be, yeah. But roughly, as a ballpark number, what we need is about 60 e-folds of inflation. So 60 Hubble times of inflation in order to explain why the universe is so flat and so homogeneous today. Okay, for flatness and horizon problem. Okay, so now let's get back to this example of m squared phi squared inflation. So we can compute our slower parameters. Epsilon v, right, was just m Planck squared over 2 v prime over v squared. Okay, we just take the derivative here, right? The m drops out, so we're just left with 1 over half, we have 1 over 2 there, right? But then from taking the derivative, we get a factor of 2, which we square, so we get 4. So in total, we get 2 m Planck over phi squared. And our condition is, right, that during inflation, this needs to be smaller than 1, which means that we can now compute the end of inflation. So the end of inflation is when this is epsilon v is 1, right? This gives us the end of inflation where the condition that omega is smaller than minus 1/3 is violated. So just plug this in here, and you get that the end of inflation occurs at the field value of a square root of 2 times the Planck mass. Okay, so this is very large field values, kind of in terms of the energy densities that we're normally used to. And so we have inflation always when epsilon is smaller than this value, which means we have inflation for phi larger than this value, right? Because then epsilon is correspondingly smaller. So now if we say we want 60 e-folds of inflation, it means we want 60 to be n of, let me call it phi start, right? So the start of inflation, we use this expression here, right, for n of phi. We plug in epsilon, which we computed here. So we're using this expression here, 1 over m Planck phi end to phi 1 over 2 epsilon d phi. We plug in our expression for epsilon, and we get from the starting point, just from this phi here, where we just plug it in, we get phi squared over 4 m Planck squared. And then from the end point, which we've evaluated already up here, we just get minus 1/2. Now, 1/2 we can ignore compared to 60, right? So you can just solve this for phi, and then you get, so this is of course phi start, right? And this is also phi start. And then you get that phi start should be about 15 m Planck. So this is 2 times square root of 60. So what does that mean? That means we have some m squared phi squared scalar potential, right? Like just like this. Whoa. And we have some value phi end at square root of 2 m Planck, and some value phi start at 15 m Planck. And our field is rolling down in this range here, right? Maybe it's also rolling already up here. That's okay. We can have much more than 60 inflations. That's fine. But we need at least 60 e-folds of inflation, right? So we need to somehow start somewhere up here, and then we roll, and then once we reach this point, inflation ends. So the message here is that kind of one of the simplest models that you can write down, really kind of first chapter Peskin Schroeder, actually has all the properties that we needed to have. It generates an equation of state which is smaller than minus 1. It can sustain inflation for at least 60 e-folds, and so it can solve the flatness on the horizon problem. Are there any questions so far?
Is there any fundamental reason to consider an scalar field and another more complex, like tensor or vector fields, or several scalar fields?
Well, this is the simplest thing you can do. You can do more complicated things. However, you need to keep in mind that what you generate is an isotropic universe. So if you do this with something which is an index, you will generate a preferred direction in the universe, and you will typically end up with an observable universe which has some preferred direction, which is not what we see. Okay, so you can do it with vectors, probably also with tensors, but you need to contract them in a way that the thing which gets the vacuum expectation value, so the thing which is effectively your scalar field here, doesn't have any indices anymore. Because otherwise you'll generate something which is anisotropic. There's another question there? I just repeat. Okay, the question is eta smaller than 1 a condition? Yeah, it's a condition. Well, it's a condition in, okay, so strictly speaking, the real condition is that you want epsilon smaller than 1, which means accelerated universe, for a sufficiently long period of time, where sufficient means 60 e-folds in order to solve the horizon and the flatness problem. In practice, if you violate the condition on eta, you will simply not manage to sustain this for a sufficiently long time. So I will always work under the assumption eta smaller than 1, because then my equations simplify. In principle, you don't have to do it, right? You can keep eta. I mean, you even don't need to work in this lower approximation, right? I mean, you can keep everything exactly. But typically, if you want a successful model, you will always have this.
One tiny thing, Valerie. I am missing a Max Planck mass factor. So when you define n of phi, at the end, at the right, you have like the integral over phi of 1 over the square root of 2 epsilon, which has no Planck mass.
But I have the d phi, right? So I have 1 over m Planck.
Yes.
And then I have the integral over d phi. D phi has units of mass dimension 1.
Right, but this 1 over m doesn't appears only in 16 below here. Sorry. So it appears here, but it doesn't appear in the top. Right?
Ah, well, okay, sorry.
So
yeah, that's because I send m Planck to 1 sometimes, and sometimes I don't. So this is the correct mass dimensions, right? Which means that I'm missing it up here, right? Yeah. So here I set m Planck to 1.
All right.
This happens when I try to restore the factors a posteriori, right? I should just not do it and just put it to 1 everywhere.
Fine. One little thing that Jorge was saying, actually, I was wondering too. 60, is this why 60 and not 50 or 70 or 30?
Well, so you can simply, I mean, we know how homogeneous the CMB is, right? So we know how much time all these 10 to the 5 regions, right, need to get into causal contact. So from that, you can compute a number. You can compute how much time you need, how much exponential expansion you need for all these 10 to the 5 regions to get into causal contact.
That must be a definite number, right? Shouldn't that?
That gives you a definite number under the assumption of instantaneous reheating, right? Because then you need to get, so now we're just talking about inflation, right? But then you need to actually connect to the, so if you assume you have inflation and then you instantaneously connect to the radiation-dominated universe, right? Then that gives you a number. But then it depends on the details of the reheating process, which is why it varies a bit. It also depends a bit on the scale of inflation.
By the way, this is all, of course, this is all before nucleosynthesis. So there's no particles. In the universe, this is only phi right now.
This is only phi. Because even if we had other stuff, so imagine you could have a period of whatever beforehand, right? BBN, everything, right? Another entire other universe, right? But whatever you had beforehand, because of this exponential expansion, gets completely erased, right? So whatever you have beforehand doesn't matter at this point. We have to start over, which also means, as you say, like everything that we talked about otherwise, right? The CMB, the BBN, baryogenesis, we have to do this all afterwards. Okay, this sets our initial conditions. Okay, so then this is the last slide for today. And this is basically already hinting at what we'll be doing tomorrow. And that is that everything that we did today was classical theory. I just put a homogeneous field, and I told you, okay, this is the equation of motion we get for homogeneous field. But in reality, we live in a quantum universe. So we cannot just put by hand a field and say, you are homogeneous, stay homogeneous, right? There will always be quantum fluctuations. And hence, what we'll do tomorrow is we'll talk about these small perturbations. And for that, I want to say a few words about how we deal with perturbation theory and cosmology. I assume you've already heard similar things in the lectures on the CMB. So what we'll be doing is we'll be expanding all quantities in a background value and a small perturbation. And where there's x, these quantities that we will use are the field phi that we talked about today, but also the metric. Because also the metric is not perfectly homogeneous, but it can be perturbed by small fluctuations. And then everything that we will do will be working in linear order in these small perturbations. And the advantage of doing that is that at linear order, you can do a decomposition into scalar vector and tensors, where scalar vector tensors mean, am I looking at an object which is 0 indices, 1 indices, or 2 indices, right? So it's the behavior under spatial rotations. And at linear order, these completely decompose into 3 separate sectors. And here, today and tomorrow, we will only be talking about the scalar sector. So we'll only be looking at the scalar perturbations during inflation. And the vectors and the tensors, they evolve independently. So we can treat all 3 sectors independently. And the degrees of freedom in total that one would be dealing with is, so for, we have then in the delta phi, right? This is a scalar. So there's 1 scalar degree of freedom inside. That's a bit obvious. But then I said we also have the metric. And in the metric, there's actually 4 scalars, 2 vectors, 1 tensor. So if you add them all up, you get 10 degrees of freedom, which is what you would expect from a 4x4 symmetric tensor. These tensors here will be the gravitational waves. That's what sources gravitational waves during inflation. We won't have the time to talk about them in any detail, but that's another independent way of trying to probe inflation. The vectors we will ignore for the rest of these lectures, because the vectors, even if they are generated on cosmological timescales, they decay. So they typically give no observational signals today, so we will just ignore them. And the scalars, they do something interesting. So there's 1 scalar in the scalar field. There's 4 scalar degrees of freedom in the metric. However, out of these 5, only 1 is physical. Where with physical, I mean that it's not a gauge degree of freedom. Where with gauge, what I'm referring to here is the coordinate transformations of general relativity. So, of course, I can write down a theory, I can write down some perturbations, but then I need to make sure that my observables are invariant under coordinate transformations. And in particular, you can imagine that, okay, when I define a perturbation and I define a homogeneous background, it depends a lot how I do my time slicing, right? If I define a time slicing, then I measure inhomogeneities on this time slice. But if I define a different time slice, then my homogeneities will look different. In particular, you could even imagine you have a perfectly homogeneous universe, but you put in a weird time slice, which is kind of wobbly, then it would seem, if you now look at on this time slice, what is the background value in the perturbations, you would seem to have perturbations. So this is why when you do this expansion, when you linearize gravity, what the value that your perturbations take depend on your gauge choice, right? And one way of visualizing is to say that it depends on your time slicing. So this is a well-known problem, right? And to deal with it, you have 2 options. So one is you can do everything in the most perfect way, right? And you can define, you can think about the problem and you can define a gauge invariant quantity. And then you do all your calculations just in this gauge invariant quantity. And for these scalar perturbations, one of the most commonly used scalar quantities is what is called the co-moving curvature perturbation. So that's the spatial curvature measured on hypersurfaces which have constant value of the scalar field. During inflation, it's defined in this way. So psi here is the Newtonian potential in the metric, and del phi is the perturbation of the scalar field. So that's one way to do it. And the other way to do it is if you trust yourself, right? Then you can also just choose a gauge. And then all your intermediate results may be gauge dependent, but your final result, which is a physical observable, has to be gauge independent. right? So it's also okay to just choose a gauge as long as you don't make any mistakes. That's completely fine. And actually, that's kind of the simpler option that we were working with tomorrow, which is why we'll be only dealing with one single scalar degree of freedom to quantify all the scalar perturbations generated from inflation. Okay, that brings me to the end for today, and I'm happy to take any questions. Maybe just briefly before we go to questions, you have to tell me what is better, bad lighting or bad handwriting. So who prefers we do tomorrow on the blackboard? Okay, who prefers we do tomorrow here? Okay, that's clear. You like my bad handwriting. Okay, fantastic. Okay, now questions.
So thank you. Actually, the potential with the m square seems like if you add maybe a lambda phi to the fourth term, a Higgs potential, something like that. So you can do a Higgs inflation, I think so. But maybe I am wondering, could be an spontaneous symmetry breaking in the inflation? Like actually seems so, or appears in the Higgs potential for the standard model?
I'm not quite sure I understand the question. So you can, yes, so this is just the simplest model, right? And you can do more complicated, and of course it's a very valid question to think, okay, we have one scalar that we know of in the standard model, right? Can it do the job, right? The current answer is that at the moment, with what we know at the moment, it cannot do the job just by itself, simply because the parameters of the Higgs potential are measured, right? At the level of what we discussed today, just given off inflation, it would work. But what we'll do tomorrow is we'll compute the predictions for the CMB from the perturbations, right? And then you have to see if in this case, if the parameters of your model, in this case we just said M, right? If that's actually sufficient amount of freedom to match all the observables. And with the parameters of the Higgs potential that we have measured, it simply doesn't match the data by itself, right? You have to extend.
Yeah, thanks for the talk. Regarding this last example, how can we extract information about the mass of the field?
Tomorrow. So from this we cannot, right? So from this kind of the mass is still a free parameter. But tomorrow we'll look at these perturbations and we'll compare these perturbations to the observations in the CMB, and from that we can extract the mass parameter.
Okay, thanks.
And even more, we will find the model doesn't work, but. But for one day, you can believe that it works.
Thank you for your talk. My question is about the last lecture, actually. You mentioned a mechanism for having baryogenesis via helical magnetic fields. And I'm not sure I understood pretty well. I was wondering if these magnetic fields should be generated precisely during the electroweak phase transition due to the spheral mechanism, or they could even be there like from the inflation.
Yeah, so they should be there before the electric phase transition for this mechanism to work, right? But they cannot be there before, if they were there before inflation, they were completely erased, right? Because again, magnetic fields are radiation energy density. If you have an exponentially expanding universe, energy density just gets completely depleted. So we still need a mechanism after inflation, but before the electric phase transition, to generate these helical magnetic fields. And it's not trivial, right? Not at all trivial, but there are ways to do it, and there's even suggestions how to kind of do it. Maybe we can discuss a bit in more detail offline, but there's even ways how to do it, just kind of starting from thermal fluctuations to build up these helical fields.
Okay, regarding the counting of the degrees of freedom for the metric, I think I got a little confused, maybe I missed it, but I thought that with coordinate transformation or gauge freedom, you can remove up to 2 scalars and not 3, right?
The thing is, you have two transformations that you do, right? So first you go to Lorentz gauge, and going to Lorentz gauge, you can remove 2 scalar degrees of freedom. But even when you're in Lorentz gauge, you still have a residual gauge transformation. It's basically the same as in electromagnetism, right? Also in electromagnetism, you go to Lorentz gauge, But then you still have, if we talk about electromagnetism, you still have a residual degree of freedom where you have a box a mu equals 0. And any a mu that satisfies that, right, is still a solution to your equations of motion. And so with that, you can, and here you have the same thing, right? So you can remove 2 times 2 scalars. So you can remove 4 scalars in total.
Ah, okay. No, because if you count there, no, you have like 10 degrees of freedom, like because the metric is 4 times 4 and it's symmetric.
Yeah.
And then by coordinate transformation, you can remove up to 4 degrees of freedom, right?
No, you can, exactly. You remove 4 and you remove exactly those 4 scalars.
Okay, okay.
And then you're left with 1 scalar, right? Because you had 1 from the del phi and 4 in the metric, so you had 5 to start with, and you actually remove 4 scalars. So you have one scalar left.
Okay, fair enough, thanks.
More questions? Actually, I was confused about the same issue as well. You're saying you have to move to the Lorentz gauge, but I thought so far you were doing things gauge independently, right? And then you say you have to go to the Lorentz gauge in order to remove these degrees of freedom. I'm getting lost a bit.
Okay, so what I'm saying is, if you just count, if you don't do any gauge fixing, right?
Right.
You have 10 plus 1 degrees of freedom.
If I say I'm there, I have 4 plus 2 plus 1, that's
No,
0.
but this is two vectors, right? Means 2 times 2.
Okay.
So because the vector is 2 helicities, the
So
tensor
it's
also
10,
is 2
okay.
helicities, so this is 10, right? And then you also have 1 here, so you have
Okay.
11 total.
Okay.
And you could work with these 11 degrees of freedom, right? Then you would do it in a completely gauge invariant way. But I also want to ask the question, okay, I would like to know how many of these degrees of freedom are gauge degrees of freedom and how many are physical, right? So I can imagine what is the maximum amount of gauge fixing that I can do. And if I do the maximum amount of gauge fixing, I can remove 4 scalars.
Okay.
So then I'm only left with 1 scalar.
Okay. 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 Just one thing. Why do the vectors decay?
The vectors decay because simply if you look at, okay, so we'll see tomorrow. So I think that what you should really be asking is why do the scalars don't decay, right? Because I mean you're in an expanding universe, and normally everything decays, right? So what we'll see tomorrow is that the scalars don't decay, even on cosmologically long timescales, because they do something which is called freezing out on superhorizon scales. And I'll explain what that is tomorrow. And the tensors have the same property, and the vectors do not have that property. So the vectors actually do exactly what you think they would do. If you generate a quantum fluctuation 13 billion years ago, right? Then it decays away until today. So the vectors are doing exactly what you think they should be doing, right? It's the scalars and the tensors that are doing something weird.
Okay. Okay. One last question. So we yes.
I mean, if there's more questions, you can also ask me in a coffee break or also on Slack.
Hi, thank you for the lectures. I was wondering, at the end of inflation, we have an empty universe with this scalar field, and then how the standard model particles are generated from that. Thank you.
Yeah, that's a very good question, right? Can give another lecture. Okay, so in this m squared phi squared model, what you can imagine is simply that you introduce a perturbative decay, say Yukawa coupling, to some of the standard model particles, right? And then as the field, after the end of inflation, the field will start oscillating around the minimum. And as it oscillates, it can decay into the standard model particles. And that way you will generate high energetic standard model particles, which then talk to each other via fast gauge interactions and generate the hot thermal plasma of the early universe. But you're absolutely right that one of the, and that's actually a very non-trivial point, because as soon as I add interactions with the standard model, I add loop diagrams to my physics, which means that I now need to go back and think about, okay, I said that my potential has to have certain properties. Now I need to check if the loop corrections actually still satisfy those properties, right? So it's non-trivial, but it's definitely something you need to think about if you build a model of inflation. You need to think, how in the end do I get my energy from this sector, from the vacuum sector, into the standard model sector? So there needs to be some channel, at least gravitational, right? But there needs to be some channel how this new field, that's called the inflaton field, how that talks to the standard model.
Okay, thank you very much, Valerie, and thank you everyone for the discussion. let's welcome Francesca to the stage.
Okay, so welcome back for the remaining part of my lectures about how using cosmic and gamma rays to probe fundamental physics, more generally new physics. So what we have seen yesterday was this broad introduction about cosmic and gamma rays, how they are produced, they are transported in the galaxy, and how really the multi-messenger connection can make the link between different mechanisms for acceleration and production of cosmic rays. We also started to see a bit about dark matter, what are the general ingredients that we need to look for it with indirect probes, and more generally astroparticle observables. And today we'll keep on going with particle dark matter, but at heavier masses with respect to yesterday. And then we'll touch upon other two candidates that you have heard of in the other lectures, so primordial black holes and axion-like particles, which not necessarily are related to the dark matter problem. And finally, if there is time at the end of the second hour, I'll touch upon some anomalies that do exist in cosmic rays and gamma rays and how we can tackle them and try to find some solutions. So this is a recap slide from yesterday, where I've been discussing only this bit of the dark matter mass parameter space. So if dark matter is lighter than the threshold for production of electron and positrons, then you only expect it to decay into 2 photons. And since dark matter is at rest in the halo of the Milky Way, we really do expect the photons to be emitted back to back. So we do expect a sharp line feature at around the mass of half of the mass if this is of the particle, if this is a decay process. So today what we will see is how we can really try to look for dark matter signals that are broader in energy. And this occurs when you start to open up other channels for annihilation or decay. So the mass of the dark matter particles should be larger than the threshold for production of electron positrons, at least. And you have a broader energy spectrum. So here, this broader bumpy spectrum here, where you always have a line. So this is the line you will always expect in all models. You have this broad energy emission, and we'll see from where does it come from, and then you can have final state radiation. So let's talk about the general formalism. So what you have is that dark matter mother particle can decay, or 2 dark matter particles can annihilate, and they do so in a given final state. Final state from the standard model, which can be quarks, leptons, or bosons. So those are not stable. They will decay and hadronize through standard model physics. There is nothing exotic here. And they lead to observable signatures of some particles which are stable and that we can target with cosmic ray observatories. So we can have photons of different wavelengths, for example, or electron and positrons, or antiprotons and neutrinos. So let's just have a look at one typical channel for annihilation. So whenever you hear the sentence final state, we refer to the intermediate final state here directly from the first step of annihilation. So final state can be, for example, pairs of bottom and anti-bottom quarks. And if you have dark matter to annihilate into those particles, then what you do expect as final stable products after these standard model showering and anodization processes are different particles. So you do expect a fraction of it to go into photons, a fraction to go into electrons. The most dominant in this case, depending on the mass of the dark matter particle, are neutrinos, and then a little bit of protons and deuterons. So this is only determined by the center of mass energy, so twice the dark matter mass if you have the annihilation or the dark matter mass, and the standard model. And you can derive those final stable particles through event generators like PIFIA, for example. More generally, we refer to the number of, for example, photons that are produced per interaction as a function of energy for each given final state. And if you have a full model for your particle dark matter candidate, what you do predict, starting from your Lagrangian and the coupling with the standard model particles, are also those branching fractions. So you always know, more or less, given your model, what is the fraction of dark matter particle that will go into big quarks, what is the fraction into leptons, and what is the fraction into bosons. However, when we do dark matter searches in a more model-independent way, we don't really know what kind of model we want to we live in. And so what we do is that, as a matter of fact, we fix the branching ratio to 1, and we study the constraint or the discovery potential of your data as a function of one of those channels. So, for example, big quarks and taus, and you will see a bit why. But you can always recast whatever results from indirect detection into your preferred model, where you plug in the real spectrum as you expect from your theory. You can also do something analogous for taus and for electrons. And just to have a look here, so if you have taus, they have semi-hadronic decay, so you also do predict photons from pion decay. And if you have electrons instead, they only can produce electrons, and you can have a minimal decay into final state radiation. So let's have a look at the spectra that you typically have. Those are cast in a dimensionless quantity. This X, which is the energy of the photon, for example, divided by the mass of the dark matter particle. And all the spectra are cut off at 1 in this dimensionless variable because of the kinematic limit of the mass of the dark matter particle. So you cannot, in an annihilation, you cannot produce more than with an energy larger than the mass of the dark matter particle. And then this is just to show how two spectra look like. So here you have the spectrum from big quarks. This is rather smooth. And what we say, it is softer than the spectrum from taus. So the harder is the spectrum, the more photons are at higher energies. So the taus, because of this semi-hadronic decay, they can reach higher energies. So the photons produced by the tau annihilation. So you will find often those two typical channels used in the literature because those are the two extreme spectra that you can have for dark matter annihilation or decay. So all the other quarks spectra do look more or less as the big quarks, also the Ws and the Z, but and the taus and the electrons and muons more or less looks the same. What really makes a difference from a pheno point of view is the behavior, so this, the energy dependence of the number of particles produced. So the fact that one just is softer than the other. So more generally, you have, as I said, different contribution to this spectrum. So these are the contribution from the decay and anodization of quarks and bosons, as I mentioned before. But then you do expect always the line. And depending on the models, your line can be suppressed. So generally, the line signal is suppressed with respect to the quark emission because the line is predicted to arise at loop level. But you can also have other spectral feature, like, for example, the virtual internal bremsstrahlung, whenever you have a photon which is emitted either from the final legs of the, for example, pairs of leptons emitted, or the internal mediator leg. And you have, when we say spectral features, it means that we do expect some characteristic behavior of the spectrum that cut off abruptly at the end of the mass, of the energy range, so around the mass of the dark matter particle. Why are those features interesting is because they are like a unique expectation for dark matter models, while this featureless spectrum here can be often degenerate with other astrophysical backgrounds. Those spectral features are uniquely identifying a dark matter signal. So there are searches that do leverage on those spectral features in order to increase the sensitivity to a dark matter signal and also boost a bit your constraining power. As I mentioned before, there are numerical tools that have been written and that you can use to derive the spectra from dark matter annihilation. So I'll just mention a few. So you can use dark SUSY and micromega. Those are more complex tools in general to make dark matter phenomenology, for also making some complementarity study between collider direct and indirect detection. You have the Poor Particle Cookbook for Dark Matter Indirect Detection, where you have Mathematica and Python tables where you see tabulated all the spectra for different masses of the dark matter particle, and that can also be used. They also have implemented the computation for inverse Compton and synchrotron emission from dark matter, which might be of relevance for some work. On the other hand, you can also use some analytical fictive functions. Those were works in the early 2010s, where they approximated the numerical results from FIFIA with analytical formulae, and whatever you want to do some back-of-the-envelope estimate, you can use those directly. There is a bit of uncertainty, systematic uncertainty in the spectra, which comes from what event generator you have been using for the standard model parts, so the decay and hadronization. And the uncertainty runs from about 5% up to 30%, depending on the study, but it's something to take into account. So as for the dark matter decay, we have seen yesterday a more general introduction. Here is the slides for dark matter annihilation. So the rate, you can write it exactly in the same way as for the decay, but now what you have in this case is that you need to compute what is the number of pairs of dark matter particles that do come together to annihilate. And the probability of the interaction, so the strength of the interaction, is given by this annihilation cross-section average over the velocity distribution of the dark matter particles, which makes directly the link between today and the early universe. And then you have this term, as it was for the dark matter decay, of the spectrum, so the number of particles produced per annihilation in this case. The number of pairs can be directly recast into the energy, dark matter density, and the mass of the dark matter particles with a factor which depends on the fact that the dark matter particle is a Majorana or a Dirac particle. So you see here what I mentioned yesterday, that the rate for annihilation depends on the dark matter density squared. So any uncertainty on the dark matter density is really important here because you are using the square of it. And to go from the rate to the isotropic flux, you need to integrate over the solid angle and the line of sight. And you have a very similar expression to the decay, where you have this part here, which is related only to the particle physics model that you deal with, and this bit here, which is called often the J factor, which is only a geometrical factor that accounts for the distribution of dark matter in the target of interest. So I mentioned this link with the early universe, but and this equation here, what I want just to mention is that you have to be careful that in MOS model, the cross-section, the annihilation cross-section is effectively velocity independent, but more general models, what you can do is to expand the cross-section into different velocity terms. So you can have an S wave, which is a velocity independent, or generally a P wave, which goes as a bit square. And if your cross-section for your given model is velocity independent, then this equation breaks down. So what you need really to do is to integrate the full cross-section and dark matter density over the velocity distribution of your particle in the halo. And so you receive a contribution in this integral that comes from the velocity dependence of the cross-section. But in more generally, in the non-relativistic regime, if the cross-section is present, the S wave is always dominating. So except if you have suppression effects like helicity suppression, where you have a linkation into fermions and anti-fermions pair, you are safe by just using the velocity-independent approximation. So if we go ahead this way, then we have a way to compute the spectrum, and we can go to the flux space then. This is just a sketch of what you would expect in the flux space versus energy, where I just depicted here some data on some background power law model. And your dark matter signal multiplied by E square would look like a bump, more or less centered at the value, or let's say ending at the value of the dark matter mass. Increasing the dark matter mass can move your signal at higher energy, and the cross-section is your normalization factor. So it does, increasing the cross-section, you boost up your signal, the same way decreasing it fades down your signal. As for the geometrical factor, if you were to compute what is the expected gamma ray map from this kind of process, you would expect something like this for a typical Caspi profile, so a Navarro-Frank-White profile here, where you see it is a very smooth signal that doesn't not have strong spatial features except for the bright spot at the galactic center. And as I mentioned yesterday during the Q&A session, the fact that we really don't know how to extrapolate the dark matter distribution towards the center of the galaxy makes the uncertainty on this geometrical factor pretty severe when we want to compute this flux towards the center of our own galaxy. So it's another theoretical uncertainty to take into account. Yesterday I described that whenever we have leptons in cosmic rays in general, you also have production and generation of photons through the interaction of those leptons with low energy ambient photons from the, for example, interstellar radiation field of the CMB, the starlight, and the infrared light. So this is the inverse Compton, and the same is true also for dark matter, because whenever with dark matter annihilation or decay, you end up having leptons produced, those leptons do not only contribute to the corresponding signal for of charged cosmic rays like positrons and antiprotons, but they also contribute to the photon signal. And the photons can be produced through the mechanisms of standard astrophysics that I described yesterday. So if you have this low energy ambient photon from the interstellar radiation field that just scatter off a dark matter electron, then you can produce gamma rays, and the final energy of the photon is related, as I mentioned yesterday, to the energy of the electron and the energy of the low energy ambient field photon. So if you typically have dark matter mass around the GeV to TeV scale, again, you would expect that for typical values of those standard radiation fields, you produce photons at GeV to TeV energies. You can also have Bremsstrahlung. I mentioned that yesterday. This is a contribution to the galactic diffuse emission. But again, if you have an electron produced by dark matter, it can undergo the very same process by interacting with protons of the interstellar medium and leading to the production of photons. Also, the synchrotron radiation is pretty important because, again, you do expect electrons from dark matter to radiate photons when traveling into the magnetic field of the galaxy. So for typically electrons at the GeV to TeV energies, you have photons in the radio band at megahertz to gigahertz. So as you can also notice, for the inverse Compton, this gives you a bit of more leverage on the dark matter masses that you can probe, because in general, when you have inverse Compton emission, so this is the inverse Compton power as a function of gamma ray energy, you can probe with inverse Compton masses that are slightly higher than the nominal energy at which, a nominal center of mass energy. So let's suppose that you have a 10 GeV dark matter particle, but you would expect to have photons only at tens of GeV, but as a matter of fact, because of inverse Compton it relates photons through this formula, and depending on the energy of the electrons, you can also have a signal in the MEV band thanks to the CMB. So you can use, for example, hard X-rays that you wouldn't expect to be able to probe masses of dark matter at the GeV scale to probe sub-GeV or GeV dark matter. And the same is if you go down in mass, if you take, for example, keV energies, then you can probe masses at the sub-GeV scale. So this can broaden a bit. So studying this secondary emission from radiative emission from leptons can help you broaden a bit the parameter space that you can probe with different observables. And indeed, the spectrum from dark matter is truly multi-wavelength. So this is again the flux, just in erg centimeters squared per second, the function of the frequency, where in the gamma ray band, let's suppose a mass of the dark matter particle around 100 GeV, you do have this prompt gamma ray emission. But because of this secondary production through inverse Compton and synchrotron, you also do expect a peak in hard X-rays from inverse Compton, and the second peak in the radio band from the synchrotron. So you can truly try to leverage onto those multi-wavelength spectrum in order to, again, increase your sensitivity to a dark matter signal. So I don't know if you have any question, otherwise I'll just move to the next part. Okay, good. Yeah.
You're dealing with electrons, but I guess it will be very similar if you have muons or something, because of decay to electrons, no? At the end
so
of the day.
the only important thing is that in the final, you have muons. You can also have muons that they do decay into electrons, and then again the electrons they do. You also have inverse Compton from muons, right. But the inverse Compton, so I don't have it here, the inverse Compton power goes like 1 over m to the 4th, and so you have a suppression by the 4th power of the mass. Mm-hmm. That's why the inverse Compton is very efficient for electrons, a bit less for muons, but not at all for protons. Okay. But in principle, you also have inverse Compton from protons.
And the taus are different because of the hadronic decay?
The taus has a semi-hadronic decay, and yet you can have the electrons that comes from the showering of the taus that still do contribute.
Okay.
So, yeah, it goes on whenever you have leptons.
Okay.
I have a very basic question, just to clarify my mind. Why do you expect that the dark matter particles also behave that baryonic matter? I mean, because you are talking about that it radiate, absorb, all this stuff, and so I wonder why.
So here we are in the context of particle dark matter. So you are within a context of models that do make the hypothesis that dark matter is a relic from the early universe. So it formed as a new particle beyond the standard model in the early universe. Then it decoupled through the thermal history of the universe. And it had couplings, and it has couplings with standard model particle. So we are really talking about specific models for dark matter, where you have these new degrees of freedom as particles that needs to be introduced in your model, and you have dark matter that interacts with standard model particles through some coupling, and those are the very same couplings that allow you to compute, for example, the Rerick abundance through this cross-section, annihilation cross-section, that gives you the right term. So we are really in the paradigm of weak scale dark matter, where you are within a given model for that. We will see that for primordial black holes, for example, you don't have this coupling with the standard model, but still you can expect some radiation for some fundamental properties of the primordial black holes. But here we are really in the context of particle dark matter, where in your model, dark matter couples with standard model particles. I don't know if this replied to your question.
In addition, actually, are we assuming that the dark matter is fermionic?
Yes, in that case, yes. So
they are
whatever.
fermion dark matter.
Yeah, either Majorana or Dirac particle. But yeah, you can more generally, you can do whenever you have. So this is, for example, for a scalar dark matter particle, those branching ratios, but is sub GeV dark matter. So the most important, so the equations are slightly different. But again, whenever you have your model that predicts coupling with the standard models, you can have your spectrum computed, whatever. And then the equation, whatever it was here, the rate. You can always rewrite your rate, right? The rate is your rate per unit energy and volume. So whatever model you have, you can rewrite this rate in such a way that match, of course, your model expectation. And this comes only from the integral of the rate over the solid angle and isotropic emission hypothesis.
Okay.
So, yeah.
Because maybe if you have fermionic dark matter, the density profile maybe could be a core, maybe, density profile, right? That this
yeah,
constant.
it might also be that you have cores in the very inner region of the galaxy because of phase space density arguments.
Okay.
Yeah. Okay, let's move on. So then this particle dark matter emission, one prototypical candidate is dark matter at the weak scale that Tracy already introduced you, from which we have this very, let's say, nice connection between the early universe and today. So indeed, you can the space for weak scale dark matter, or let's say weakly interacting massive particle, is defined by this annihilation cross section as a function of the mass of the dark matter particle, and you can use really different observables to constrain this parameter space. There is a thermal cross-section which is defined through the fact that you don't want the cross-section to close the universe, so it should be a good dark matter candidate. And then you can use the visible light, or let's say different observables from astroparticle, to constrain the value of this cross-section as a function of mass. And you have different ways. So Tracy discussed the Big Bang nucleosynthesis and the CMB. And here at more than 10 of GeV in mass is really are really the constraints from gamma rays and charged cosmic rays that can close this window. So for WIMPs, you have this direct link with the early universe, and you can recast these constraints in a consistent way in order to account for your specific model. But how we really do look for dark matter with gamma rays, and how we can draw this line? Well, the targets for dark matter searches really depends on the one hand on the signal expectation. So you want your signal to be the brightest in order to improve your sensitivity, but you also want the astrophysical background to be the lowest in order not to just contaminate too much your signal. So there are several targets that have been identified. So from the point of view of dark matter, if you have like cusps, so strong profiles, very cusp towards the galactic center, you expect the galactic center to be the place where your signal is the brightest. However, there is also large contamination from the galactic diffuse emission that we discussed yesterday, so it might not be the optimal place to look for dark matter because of the signal to noise ratio. So there are other targets that you can have a look at, so galaxy clusters, for example, or objects like satellites of our own Milky Way, which are dubbed dwarf spheroidal galaxies, and we will see in details more this example. What I would like you to take away is that whenever you want to look for dark matter, there is this guaranteed emission from the galactic plane and from all other sources that you have to account for. So the astrophysical background modeling is, again, the source of the largest systematic uncertainty that you have whenever you perform searches for dark matter in gamma rays, but also charged cosmic rays. So you have to carefully assess this kind of uncertainties if you want to make robust claims. So depending on the target of interest, so the target defines your spatial distribution of your signal, you can do a different type of searches, which can be more or less model independent. So I like to talk in general about feature-based searches, because you can leverage either on the spectral features that I mentioned before, so the fact that you can look, for example, for gamma ray lines, and for that you don't really need to account for any spatial information, in the sense that you just look for the place where the signal over background ratio is largest, and you want to look for very sharp features in the spectrum of your data. But you can also leverage on the fact that you do expect some angular correlation at different scales from dark matter rather than from an astrophysical background. So, for example, if you have dark matter subhalos, you do expect the sky to cluster at small scales differently than if you have a population of isotropic sources. So you can use cross-correlation or angular signatures, like looking for anisotropies, to try to look for this kind of signal. So more generally, whenever you have a model for dark matter, so for example, for your particle theory, you have a very predictive way to have multiple observables all together. So you can also leverage on the different direct and indirect and collider searches and break some degeneracies. But here I will just discuss indirect probes alone. So I'll focus for a bit on searches towards dwarf spheroidal galaxies, because this can give you a flavor of what is done at GeV scales. So dwarf spheroidal galaxies are satellites of our own Milky Way, more or less located 100 kiloparsecs from the solar system, and they are thought to be clean targets for dark matter because of the high mass-to-light ratio. So you expect them to host a large dark matter potential, while the baryonic physics should be very little, because they do not have enough stellar mass at the beginning to trigger strong star formation. So the number of dwarfs today is more than 50, so it reaches almost hundreds, thanks to the latest advent of digital surveys like SDSS and DES. And in the future, with LSST, the Vera Rubin survey, we do expect to discover even more. So why dwarf spheroidal galaxies are interesting? Because we actually measure what is their stellar content, and we can infer from the dynamic of the stars what is the dynamical mass, so the dark matter mass, that should be contained into those objects. So you can derive only from stellar dynamic analysis what is the expected J factor, or even, if you want, what is the dark matter mass in those objects. And depending on the type of analysis that you perform, you also have some systematic uncertainty here. You can classify dwarfs into two categories. Classical dwarfs, they contain 1,000 of stars, and so it's much easier to do dynamical mass modeling, so you have pretty good determination of the J factor with a very little systematic uncertainties depending on the analysis that you perform. But you also have a sample of dwarfs which contains only less than hundreds of stars, which are called ultra-faint dwarfs, and then the systematic uncertainty coming from the J factor determination is pretty large, because it's just enough to have a few contaminating stars that are from the foreground and not from the main dwarfs to alter the determination of the dark matter mass in the dwarfs. And why is it important to get the J factor right is because the flux directly depends on the J factor, and if you want to set constraints on dark matter or to look for a signal, then of course you end up needing to have an independent information about the J factor, so which comes in this case from optical. So then you know where the dwarf is, you know what is the J factor, you can go into Fermi data, collect the data around the position of the dwarf, and just look if there is any excess power in photons or in counts with respect to the photons that you would expect from the galactic diffuse emission or the point sources that you know around the dwarf. If there are no excesses, you, of course, can still do something for dark matter. You can set an upper limit on the sigma v versus mass plane. So far, we don't have any excess discovered in any of the dwarfs. The advantage of having many of them is that you can collect all the photons from the different dwarfs and stack them together. The fact that you stack is allowed by the fact that those are like independent targets, only connected by the same cross-section and mass if you want to look for a dark matter signal or to constrain it. So you can build a joint likelihood where you cast them all together and you improve your sensitivity a bit. So those are the limits that you would get from the single dwarf analysis. But if you combine all of them together, you gain a bit by the fact that you are not seeing any signal from the direction of all those objects together. So the current status of searches for dwarfs is the following. So in the mass plane, more or less dwarf toroidal galaxies can exclude the standard vanilla thermal dark matter model up to 100 of GeV. However, there are systematic uncertainties that can weaken the limits by a factor of 2 to 3, depending on those uncertainties on the J factor, which is especially important from ultrafaint, but also the modeling of the background from the galactic diffuse emission. So typically, dwarfs are sold as the most robust targets for constraining dark matter, and what I want to caveat you on is that yes, but there are systematics that you always have to keep into account. So let's look at a summary plot from the constraints on dark matter from 10 of GeV up to 1 TeV, where is really the LAT analysis that do dominate any other constraint. So you have that dwarfs, as I mentioned, can be affected by a factor of 10 if you account for all systematics. Then you can look at higher latitudes. So you can, for example, look for dark matter in this isotropic diffuse emission that I mentioned yesterday. And you do get constraints which are competitive with the dwarfs one. But really what dominates in this mass range are not photons, but are searches for dark matter in antiprotons and searches for dark matter at radio wavelengths. So in antiprotons, what you can do is to use the measurement of the antiprotons from IMS. And from a point of view of cosmic ray physics, you only expect antiprotons to be produced by spallation that I discussed yesterday. And the models for antiprotons production from standard astrophysics are in very good agreement with the current data. While dark matter would contribute with a primary signal of antiproton, because it can substantially have a contribution to that primary production. And you can then compare a model with a secondary antiproton plus a dark matter signal and constrain the dark matter annihilation parameter space here in blue. So the other constraint that you see here is a constraint that comes from the observation of the Large Magellanic Cloud with ASCAP, which is the precursor, one of the precursors of SKA. This is an image of the region around the Large Magellanic Cloud at about 800 megahertz. So this is radio, and what happens, so what is the physics behind this kind of constraints in that the Large Magellanic Cloud is one of the closest galaxies. You want to look for astrophysical emission from the gas in the Large Magellanic Cloud. And on top of it, you also do expect dark matter in the Magellanic Cloud to produce, for example, electrons. Those electrons would fill the magnetic field of the Magellanic Cloud itself and would then radiate non-thermal synchrotron emission. So then by making a fit to the astrophysical model for the Large Magellanic Cloud plus the synchrotron emission from those electrons from dark matter, you can set constraints on the dark matter annihilation parameter space, where the band here accounts for systematic uncertainties in the dark matter profile within the Large Magellanic Cloud, as well as the cosmic ray propagation, which is within the Large Magellanic Cloud, because you have somewhat to model the fact that electrons are produced in the Large Magellanic Cloud from dark matter, but then they do not emit synchrotron immediately afterwards. They also do diffusive transport within the Large Magellanic Cloud before losing energy into synchrotron. And depending on where the electrons from dark matter do escape, or how long they diffuse, then you do expect a larger or a smaller signal from dark matter, as it was the case for the things that I discussed yesterday for cosmic ray propagation. If we go then higher masses, so then we are in the TV mass domain, we are dominated by limits from imaging Cherenkov telescopes, and notably the observation of the galactic center with the Hess telescope, which collected about 500 hours observations of the galactic center, and it can start to constrain dark matter up to the TV scale, and touching upon the thermal relic density cross-section. So, but how can we extend this mass range in a few directions is the topic of the next part of my lecture. So we can go up in energy, and there we do have already some operating instruments like HAWK, which is very nicely giving very strong constraint on dark matter at the TV mass scale. And in the future, we do expect, as I mentioned yesterday, the Cherenkov telescope array to give a huge improvement in sensitivity. So this not only reflects on our ability to better understand the astrophysical background or describing the population of point sources, but also to have stronger constraints on dark matter if you don't find any signal, of course. So in this case, this is one of the latest CTA collaboration papers where they made some prediction for the sensitivity to thermal dark matter at the TV scale with CTA, observation of the galactic center, where you see that you can get an improvement of about a factor of 10 with respect to the current limits from Hess at starting to exclude the thermal dark matter at the TV scale. If you go to even higher energy, then you hit for thermal particle dark matter production the unitarity bound. So you cannot have any longer this kind of production mechanisms, but still you have viable candidates for dark matter that comes, for example, from the decay of the inflaton. You would expect higher mass particles to be produced, and those can decay into very high energy photons, ultra high energy cosmic rays, and more generally neutrinos. So the signal that appears in gamma rays and neutrinos can be constrained by current water Cherenkov instrument array like LASO and T-beta IS gamma, and also with IceCube. And actually the indirect detection through high energy photons and neutrinos are currently the best probes on the dark matter, heavy dark matter lifetime. So we see this kind of first part of the slides yesterday, because I mentioned that both T-beta IS gamma and LASO managed to measure the galactic diffuse emission from our own galaxy. But in this glow of diffuse photons from our own galaxy, there could also be a signal from dark matter. So you can, people have used those data from T-beta IS gamma, and now they're doing that also with LASO, to constrain dark matter model at the PV scale. Taking then a constraint, getting a constraints on the dark matter lifetime. So the game is always the same. You need a prediction from the flux from dark matter, here in black, and a prediction from your astrophysical background from cosmic rays. In order to make a combined fit to the data, here only 3 data points, which allows this much better, and get constraints of dark matter. So what I would like to mention here is that while from the point of view of the spectral energy distribution here, a signal would be allowed in the sense that the fit of astro background plus dark matter also works in describing the not so badly the data. What it really kills the possibility for dark matter to be responsible for the diffuse emission is the angular distribution of your photons. So here in red are the data points from T beta ES gamma. So this is the latitude profiles of the photons, how many photons are detected per beam in latitude. Here is what you do expect from some model of cosmic ray propagation. And here in black is the model from a CASPI dark matter profile. So as you can see, you cannot really make the data agree with your model because of the latitude dependence of the signal versus the latitude dependence of the data. So it's always important also to look at the spatial distribution of your signal compared with the data and not only to the spectrum. And I'd like to mention here that there is a very strong potential of very high energy gamma rays and neutrino to constrain heavy, let's say, PV dark matter. So watch out for this kind of instrument in the future. So now in the last 5 minutes that I have, we'll extend the range more towards the left side of this plot, where we want then to probe sub-GeV dark matter. So how to go to the sub-GeV? Well, the first thing that you can do is to then go to your instrument space and look at what kind of detectors do you have and what kind of sensitivity. So unfortunately, we are in what we call the MEV sensitivity gap, because in hard X-rays or soft gamma rays, we only have instruments that are more than 20 years old. So the spectrometerable integral here, through which we have managed to measure, for example, the spatial distribution of 511 keV photons, which comes from the electron-positron annihilation, which has a rather poor angular resolution, about 2.5 degrees. And at higher energies, you have a Comptel telescope, so Comptel, that run only up to 2000, the years 2000, and it has a decently good angular resolution, and here is the full sky map, which is nothing compared to the LAT. So really here we are limited in sensitivity, and yet there are things that can be done for dark matter. So at sub-GeV, you have only a few channels that are open for dark matter. You can have the production of lines, or through electron and positrons, gamma rays can come from final state radiation. So the observable for sub-GeV dark matter can be either to look at the glow of the diffuse emission measured with those instruments, target single objects like dwarf spheroidal galaxies, again with very deep exposure. You can also look at the 500 keV line morphology and signal, because whenever you have electrons and positrons produced from dark matter, you also do expect them to be able to annihilate with the free electrons in the galaxy and produce a line. Or you can exploit a very nice observation of the cosmic ray electron-positron fluxes that Voyager has measured in the real local interstellar medium outside the heliosphere. So Voyager has exited the heliosphere, and this is really the measurement in black from the electron and positrons. See, this is the IMS in black at GeV energies, and you always have to correct the measurements from IMS for the solar modulation, because charged particles are deflected by the solar wind. But Voyager actually exited the heliopause and managed to measure the really local interstellar spectrum of cosmic rays. So you can use those low energy cosmic rays of electrons and positrons in order to constrain like dark matter. And I'll give you just a summary plot, do two summary plots of this. You can constrain light-dark matter decay in the same way, looking for lines or final state radiation, where you see that you can use the Milky Way diffuse emission from integral, and you get the strongest constraint on the lifetime of the dark matter particle, while for decay into electron and positrons through final state is really the CMB that dominates. You can do the same for annihilation, and in this case, for masses around a few MeV, you can exploit, again, the diffuse emission from integral, while the CMB always dominates for final state radiation. So the take-away message here is that integral analysis of the diffuse emission can give you still some strong constraining power on light-dark matter decay. And so what we really would need is an MeV instrument that can fill the sensitivity gap in order to be able to constrain dark matter at the sub-GeV through this kind of mechanisms. So I stop here. For the first part of the lecture, and I'm happy to take the questions.
Questions and comments?
Hi, thank you very much. I have a curiosity, and maybe you mentioned it and I missed it. In the plots, the constraints that you showed before for dark matter annihilating, you showed the channel in B bar. Yeah, exactly.
Yeah.
If I wanted to recast those constraints with other decay channels, I would just have to look for the branching ratios of the electromagnetic part. Is that simple? Like it's just a perfect rescaling?
No.
All right.
So if you want to recast, that's a good question. So typically you only have those plots, right, when you read the papers. If you have the cross-section and the mass, what you can do, if the paper is detailed enough, is to reconstruct the flux. So this is what you need in order to recast. Let me check. Where it was that? Yeah, for example. So if the paper tells you that it excludes a given cross-section for a given mass and gives you all the ingredients that they use to compute the geometrical part, then you can get back the spectrum, so the flux of dark matter. And once you have the flux for dark matter as a function of energy, then you can recast on your model. Now, this is pretty artisanal and is not the best way to do because sometimes not all information are there. So what experimental collaborations, but also like more Fino people are doing now, is that whenever they give you the plot with sigma v as a function of mass, they also give you sometimes, now more often, the likelihood of the flux as a function of energy. So the first step, whenever you have to set constraints on some new physics, is that, as a matter of fact, you set an upper limit on the flux, and then you recast into the parameter space for dark matter by using this equation. So anyone that does data analysis, it does first, they have the upper limits on the flux at a given confidence level. So now, for example, the Fermi-Lat collaboration does that for the dwarfs, and there are other people that do this for the antiprotons. You can get the likelihood tables of the flux as a function of energy, and with that, you can then use whatever model you want, as long as you have an equation that gives you the expected flux in the same region of interest that the constraint have been derived on. So if this is the observation of the S galactic center, you have to be sure that you compute the J factor of your signal in the very same region, and then you can use your model with your branching factors and get the constraints on your cross-section.
If I might follow up just quickly, why isn't that as simple as a ratio of electromagnetic emission? Like, what changes in the propagation of...
So if you have, for example, this secondary emission from leptons, from inverse Compton, then you have to include these kind of terms. Because you just say, why I cannot just simply make the ratio of the phi1 divided by phi2. So this is correct if you only have... so there are two things. So it's correct only if you have one branching factor at the time and the spectra are similar. Because when you, let's see, when you have, no, sorry, yep. Here. Let's suppose you have, you want to recast a BB bar result into a tau tau result, right? So you take the constraints that are derived with this line, but the constraints are a joint likelihood over different energy bins. So you have your data in different energy bins. So it might be that for a BB bar, which in this plot it would look like something like this, because it's multiplied by e squared, the bin that sets the limit is this one. But if you have a harder spectrum, like tau tau, the bin that would set your limit, the tau tau would more look like this, I mean much harder. So it can be this one, for example. And so there might be biases doing so. If you want just to check, is my model constrained or not, in a sense, do I need to go further and do a more precise analysis, then yes, you can just do the ratio. But if you really want to derive the right limit, then you have to take into account that since it's a broad energy distribution, the bins that sets the limits might be different. So that's why you need the full bin information, for full energy information. And on top of that, for leptons, you can include inverse Compton, and this will increase your signal, and so make the limits stronger with respect to Bs that do not have a strong electron components, for example, so not a strong inverse Compton. You're welcome.
Hi. I'm not very familiar with sub-GeV dark matter, but how do these limits compare to collider searches?
Okay, so the point of collider search, so let's say, where it is. Yeah. So typically, collider searches for light-dark matter are focused on models which are, for example, dark sectors or variations of dark sectors, where you already have built the model in order to evade the constraints, most notably from the CMB. So those limits, in particular the one on the annihilation cross-section, are here for a cross-section which is velocity independent, so the S wave. The CMB are very strong for S wave processes, but they are not so strong for P wave processes because in early universe, the velocity of dark matter particle was much higher, and you have a suppression of V squared. Now, all those dark sector models that are looked at LHC, for example, in colliders, they do evade the CMB by construction. So in a sense, if you were to build the basic model for a portal with a S-wave, then you would hit the bounds from the CMB. And so that's why most of those models with an additional dark mediators, they do have P-wave annihilation, where those limits relax, but with if we will ever have this MEV instrument closing the gap, then there are several works, notably from Profumo and Coogan, that show that you can close really the window for P-wave dark matter processes, and so you would exclude most of those dark sector models that are now investigated at LHC, but it's not the case now.
Okay, and so you show us that different experiments and astrophysical sources can constrain dark matter in different energy regimes, right? But I wonder if is there any experiment trying to constrain dark matter in the dark epoch? I mean, after CMB and before reionization.
Yes, I'm not an expert on that, but you can look for the 21 centimeter line, for example. In this case, you would expect a signal from dark matter, and the 21 centimeter line will be measured with very high precision with, for example, SKA. So you can do either precision cosmology or also look for those kind of very dark epoch where this kind of universe, which is really today universe, cannot tell you much.
More questions? I have one too. You showed one constraint from the Large Magellanic Cloud on radio. So it was just the large, actually it was quite constraining, and I'm surprised the only one is on Large Magellanic Clouds. Question one is whether they have applied similar studies on the dwarf galaxies that you were showing before. And the second part of the question is, I remember that 10 years ago there was this radio experiment called Arcade, which found an excess at around 1 gigahertz or so, and it was interpreted as evidence, possible evidence for dark matter. I'd like to know whether there is any update on that front.
Yeah, first, so about the LMC constraints, yes, they are pretty surprising. So why you don't get such strong constraints from dwarfs is because in dwarfs, first of all, you don't know, there is a very little baryon content. So in the first place, you don't know what is the magnetic field. You are not even sure that magnetic field can form in dwarfs. So, and above that, you need electrons not to escape freely, but to have some diffusive transport before escaping. So in dwarfs, even if you assume some magnetic field, and then you make some diffusion approximation, given the small content of ESM that you have within, you have basically free escape. So there are works that try to set constraints on dwarfs, but since we know so little about cosmic ray propagation, and in general the content of the baryonic part in dwarfs, you have very large error bars and are not so constraining. So the LMC is so constraining before first ASCAP gave a really great image, because we have new measurement of the magnetic field polarization, so we know a bit better what should be the magnetic field, and we also have the tracers for the gas in the LMC. So again, we can make some model for the diffusion. And here I want to mention that it's pretty conservative, because they assume the same diffusion coefficient as the Milky Way, while the diffusion coefficient of the LMC should be slightly lower, so it should higher, so it should trap the electrons more than what is assumed here. So I think in the future would be worth having a look at the small Magellanic Cloud, perhaps. And having a better determination of the magnetic fields. I know now, for example, with Meerkat, there are at least 6 new pulsars discovered within the LMC, so you can measure Faraday rotation, and you can then infer with more accuracy what is the magnetic field. But yeah, they are pretty surprising, I think, and some room to investigate better the power of really radio. And the other question was the Arcade excess. So it's been some times that I haven't read anything about Arcade. So there was indeed this excess. I think there is still debated the fact that it might come from from some emission from really the atmosphere. And in terms of dark matter, yeah. There were some models, but that could fit with dark matter. But in the end, I think they were then later excluded by other complementary constraints. We can look up for the references, because it's been quite some time, and I think it's still there in a sense. So it hasn't been disproved by Arcade itself.
Thank you. So let's thank Francesca again.
Thank you.
Just 2 announcements, or 1 announcement at least. So the one that is, so for those requiring the certificate today, please head to the desk at the end of the room. Right, there are like 2 people flying tomorrow early, and they require some early certificates. Otherwise, certificates will be provided tomorrow. And just to confirm that on Friday the public lecture will be at 5:30. And dinner is.
And dinner, it's in the timetable is set to be at 7:30, but we'll start at 8. Okay, but please don't arrive late, so we're gonna start with aperitifs and everything. Okay. Okay. We're back in 30 minutes, more or less.